In this example, we are going to find the exact value of each of the following, or state that it is undefined. Starting with the first one, arc sine of 3 pi over 4. Now, when dealing with inverse functions applied to the original function, a lot of people are tempted just to cancel out these functions and say that the answer is just 3 pi over 4. Because a lot of times in mathematics, that is usually what you do. If you're multiplying by 3 and dividing by 3, then they just cancel out. However, that's not exactly true in all of mathematics. For example, when you're dealing with exponents and roots, that's not exactly going to be the case. Same is true here with inverse functions. Arc, cosine, and sine, in this order, will only cancel out if the angle measure you're working with here on the inside is part of the range for arc sine. So, remember that arc sine of x has to lie between negative pi halves and pi halves. If the angle measure for arc sine is within there, then we're okay. But 3 pi over 4 does not exist between negative pi over 2 and pi over 2. Meaning the answer is not just going to be 3 pi over 4 here. If that's the case, then just work from the inside out. Evaluate the inside for sine of 3 pi over 4. Sine of 3 pi over 4, 3 pi over 4 being in quadrant 2, means that we get a positive ratio. And sine of pi over 4 for a positive ratio would be square root of 2 over 2. Then work with arc sine of that ratio. Keep in mind that arc sine can only give you something between negative pi halves and pi halves. So, something that's basically in quadrant 1 or 4 of the unit circle. Because this ratio is positive, I know I should be getting something in quadrant 1, where sine is positive. And the value in quadrant 1, where sine equals square root of 2 over 2, is at pi over 4. So the answer for this first one is pi over 4. For the second one, we have a mix of two functions. We have arc cosine of sine of negative pi over 3. In this case, you definitely cannot just cancel functions. You can sometimes do that when they are a function and its own inverse. Sometimes. But here, no. In this case, just like the previous one, work from the inside out. So, evaluate sine of negative pi over 3. That would be in quadrant 4 where sine is negative, so we get a negative ratio. And sine of pi over 3 is square root of 3 over 2. When evaluating this now for arc cosine, I see my ratio is negative. And since arc cosine is defined from 0 to pi, or angle measures in quadrant 1 or 2, this would have to be an angle measure in quadrant 2 because cosine is negative there. Can't be quadrant 1. So it's going to be a quadrant 2 angle measure. It's a quadrant 2 angle measure where cosine equals negative root 3 over 2. That's going to be in the family of pi over 6. Angle measure over in quadrant 2 that involves pi over 6 is 5 pi over 6. For the third one, we have cosine and arc cosine. Again, people are going to be tempted to just cancel those out. And when done in this particular order, that actually happens to be fine most of the time. The only thing you really need to check is that the ratio actually defines a realistic triangle. This is a ratio for cosine. And cosine as a ratio is supposed to be adjacent over hypotenuse. If my ratio here is negative 3 over 2, this implies that my adjacent side for the right triangle is larger than the hypotenuse side for the right triangle, which is impossible. That cannot happen. Meaning that this ratio is an invalid ratio for cosine. So this is not anything that exists. When you put a ratio inside of an inverse function, in terms of arcsine and arccosine, it would have to be between -1 and 1. And -3/2 does not exist between -1 and 1. For the next one, I have sine and arccosine of -5/8. That ratio does exist. That ratio for arccosine implies the adjacent is 5, the hypotenuse is 8. That's a realistic triangle. Unfortunately, it's not a triangle for an angle measure I'm aware of. I don't know 5/8 as a ratio from the unit circle. So it's hard for me to evaluate what angle measure this is and then take sine of that angle. Instead, what I'm going to do is, for the time being, I'm going to call that inside, I'll just call that A for now. It is A for some angle measure that I don't know the value of. However, like other examples we've seen in this class, I don't need to know the value of it, I just need to know where it is. And I have arccosine of a negative ratio. Well, arccosine can only refer to angle measures in quadrant 1 and 2, between 0 and pi. And because it's a negative ratio, it would have to be in quadrant 2. So really, this was referring to a triangle in quadrant 2, specifically an angle measure in standard position for A in quadrant 2. And I could draw a right triangle down in quadrant 2 to represent A, or really its reference angle. I'll call it A prime, but I'll use A for simplicity. For that triangle representation, cosine being the adjacent over hypotenuse, as I've already said, means that I'll have 5 as the adjacent side of that angle measure, 8 as the hypotenuse, and in this case, 5 is negative. That's where -5/8 comes from. So, I don't know what that angle measure is. I know it's in quadrant 2, and I know 2 sides that it would relate to. If I can find the third side here, the opposite side, then I can define sine, which is opposite over hypotenuse. So, if we find this opposite side using the Pythagorean theorem, it would be 8 squared minus -5 quantity squared. That would be 64 minus 25, so that's 39, under a square root. That would end up being positive because it is in quadrant 2, so the y value should be positive. And since I just need to know sine of that angle measure, which is opposite over hypotenuse, I can define this as the square root of 39 divided by the hypotenuse side of 8. That would be my answer there. So in some of these, you don't need to know the ratio, you just need to know where it is. The same is going to apply to the last one. For the last one, we have cosine of arcsine of -8/10 plus arccosine of 5/13. So that looks a lot more complex, and again, it's referring to ratios that I don't know from the unit circle. So I don't see 1/2 or √3/2 or anything like that. So I'll just call these A for that first angle measure. I'll call this one B. So I'm really trying to determine what cosine of A plus B is. Well, when you know it, cosine of A plus B, that's something that I can use the sum identity of cosine for. The sum identity for cosine there would be cosine of A times cosine of B minus sine of A times sine of B. So this is going to work just like the previous part of this problem. As long as I know sine and also cosine of both A and B, then I don't actually need to know what A and B are themselves. So I'm also going to draw another picture for these. Scroll that down so I have a little bit of room to do so. For the angle measure A, I have arc sine of negative 8 over 10. Well, arc sine should be an angle measure between negative pi halves and pi halves. So that's either quadrant 1 or 4. Because that is a negative ratio, can't be quadrant 1, it would have to be quadrant 4. So I will draw to represent A to be an angle measure in quadrant 4. And I'll draw a right triangle to represent this. For sine, opposite over hypotenuse here would be negative 8 and 10 respectively. And if I can solve for the adjacent side, then I'm good to go. The adjacent side, you can use the Pythagorean theorem if you so please. However, you may also recognize that this is actually a 3, 4, 5 Pythagorean triple. The values are just doubled here. That adjacent side you will find will be a positive 6. Again, you can use Pythagorean theorem if you need to for that. For the other one, for B, I have arc cosine of 5 over 13. That one's a positive ratio. And arc cosine is defined from 0 to pi. So quadrant 1 or quadrant 2. Because it's positive, it would have to be in quadrant 1. So B is somewhere in quadrant 1. And again, we'll represent that with a right triangle down to the x-axis. Where for cosine, we have adjacent of 5 and hypotenuse of 13. If we can solve for the opposite side, then we should be good. You can use Pythagorean theorem again for that purpose if you so please. However, this is also another Pythagorean triple. This would be a 5, 12, 13 triangle. So this side here is just 12. Using all that information, we now should be able to put in our values. For cosine of A, looking at my first triangle, cosine is adjacent over hypotenuse. Thinking about the reference angle realistically here, the adjacent side would be 6, the hypotenuse side is 10. If you want to simplify that to 3 over 5, you may. Cosine of B, on the other hand, was actually provided to us from the get-go. The adjacent side of B is 5, the hypotenuse is 13. Then we're going to subtract sine of A. Looking at A, sine of A would be the opposite over the adjacent. Again, we had that from the beginning, would be negative 8 over 10. The opposite of the hypotenuse, I should say. And then sine of B, when we had to solve for, the opposite side of B was 12, and the hypotenuse was 13. Multiplying through accordingly, that gives us 30 over 130 plus 8 times 12 is 96 over 130, which would simplify to 126 out of 130. Or, if you want to simplify that even further, could also say 63 out of 65. That would also be fine.